All right, this is my lecture from my notes on mechanical equilibrium. This is the section that we're on right now, so equilibrium. An object is in mechanical equilibrium, when the following two conditions are true. The external force is zero. The net force external net force is zero. And the net external torque is zero. Let's think about what those statements mean. So the sum of all the forces in the x direction will equal zero. The sum of all the forces in the y direction will equal zero. And since the sum of the forces equals mass times acceleration, that means acceleration in the x and acceleration in the y is equal to zero. Since the net force is zero in the x direction, acceleration is zero in the x direction. Since the net force is zero in the y direction, then acceleration is zero in the y direction. Okay, the sum of all the torques is equal to zero, which, although you haven't seen this just yet, this is very much similar to Newton's second law, except for in rotational world. The sum of all the torques is equal to, I call that rotational mass. It's called rotational inertia. The inertia times its angular acceleration. Look at the similarities. Force equals mass times acceleration. Torque equals rotational mass times rotational acceleration, okay, or fishy thing. So again, back to where we were. Sum of all the torques equals zero. What does that mean? That means that the acceleration is going to equal, the angular acceleration is going to equal zero. That does not mean, this does not mean that there isn't a velocity or that there isn't a angular velocity. Recall that the acceleration is change in velocity over time. Angular acceleration, change in angular velocity over time. If I have a velocity of 5 meters per second and a net force of 0, my acceleration is 0, my velocity stays constant. So the change in velocity is 0, acceleration is 0. So I can be in equilibrium and be moving. It does not mean that you're not moving. It just means my acceleration is 0. Okay? So I restate that in that sentence. Read it. Think about it. The first case is when the object is in translational equilibrium. Translational is a fancy word for linear. Because the net force is 0, acceleration is 0. We've already stated that. There is no change in velocity. Doesn't mean there isn't one, just means velocity isn't changing. The second condition is when the object is in rotational equilibrium. Because the net torque is 0, the angular acceleration is 0. There is no change in angular velocity. That doesn't mean there isn't one, it just means it isn't changing. So, if I were to give you this multiple choice question, this is a way to check whether or not you understand what all that means. Which of the following must be true for an object to be in both translational, linear in other words, and rotational equilibrium? Well, hopefully you see no linear acceleration, no angular acceleration. Those two must be true. But a lot of people will come along and select there must be no velocity and there must be no angular velocity. And they'll say that it is all of them. That is not true. If I have no acceleration, if there's 0 acceleration, that just means my velocity isn't changing. Doesn't mean I don't have a velocity, just means that velocity isn't changing. So the answer for that would be B. Okay, we're going to solve a whole bunch of these problems. They're called objects in equilibrium. And there's a strategy on how to do it. So step 1, diagram, diagram, diagram. And this time we're going to have to label not just the forces acting on an object, but we need to know where the forces act relative to an axis of rotation. Why? Because torque is equal to a force times the distance away from the axis of rotation times sine of the angle between the force vector and the position vector, r vector. Okay, So draw the force diagram showing all the forces acting on the object of interest and identify the location of those forces relative to the axis of rotation. You get to select the axis of rotation. We are going to pick an axis of rotation that is convenient for the problem. What does that mean? Well, since forces that go right through the axis of rotation do not create a torque because there's no R value, we can eliminate those forces if they're unknown. So that's a way to make your life easier, okay? Doesn't really matter which location you create, no, as far as an axis of rotation, the sum of the torques will be zero about every single possible axis of rotation. What will be different is how much math and how hard the problem is based on where you select that axis of rotation. All right, then we're going to apply the sum of the forces is equal to zero in both the x and y, and that yields two equations. We will then apply the sum of the torques equals zero. This yields a single equation. That is a total of three equations with up to three unknowns. I can solve this if I have three equations and three unknowns, three equations and two unknowns, three equations and one unknown. I cannot solve this if there is three equations and four unknowns. Okay? All right, so let's do a problem. A girl of mass M sits on the left of a seesaw that is a plank of 4 meters and it has a mass of 12 kilograms. That's the plank. The young lady has a mass of 55 kilograms. This is pivoted in the middle, and we're going to assume that the plank is of uniform density, which means its center of mass is in the center. It's not got some heavier end like a hammer, for example. So let's draw what that looks like. Here's my plank. Here's my pivot, which they said was smack dab in the middle. Okay, we were told that a little girl is going to sit on the very end of the seesaw, on the left end, it actually said, and we're going to try to determine where this man is going to sit. This man has to sit, I hope you can tell, they didn't say to the right of the fulcrum, but he's going to need to sit to the right of the fulcrum some distance in order for this seesaw to balance. Now notice the man's mass is 75. The little girl's mass is 55 kilograms. So hopefully you realize that if he sat at the very, very tail end of that seesaw, since the pivot point is smack dab in the middle, the seesaw would not stay balanced and it would start to rotate in a clockwise direction and hit the ground basically. Okay, diagram and label. So we need to show all the forces acting on this seesaw. First, the girl is putting a force downward. We'll call that the weight of the girl or the force of gravity acting on the girl. We have the weight of the man that's pushing down on the seesaw. I can label that weight. I can label that force of gravity. They are the same thing. That is mass of the girl times little g. That is equal to mass of the man times little g. What else is acting on the seesaw? Well, the seesaw has mass, and the mass is located at its center of mass. And the force of gravity is acting on that. And how did I know that it was located right above that pivot point? Because it said that it is pivoted in the middle. So this is the weight of the plank, they called it. So mass of the plank times little g. Now, we're not done. What are we drawing? We're drawing forces acting on the plank, the seesaw. If those were the only forces acting on the seesaw, they're all pointing downward and the seesaw would accelerate downward. That net force is not zero. There is one more force, and that is acting upwards. The pivot point, the fulcrum, is putting a force normal in the upward direction. So we also need to identify those forces and their location to an axis of rotation. So I know I have all the information I need to calculate the weight of the girl, the weight of the plank, the weight of the mass. I don't know the force normal at this point. Now I can choose this where the girl is as a axis of rotation. I now have force normal that don't know. That would not be the best choice for that. It would make it easier if I choose the pivot point as an axis of rotation because I eliminate torque from force normal since it goes right through it. All right, so let's write our equations. The sum of the forces in the x direction, they all add up to 0. How many forces do I have in the x direction? None. 0 forces acting in the x, and sure enough, they add up to 0. How many forces do I have in the y direction? Well, I have 1 up and 3 down. Force normal minus weight of the girl minus weight of the plank minus weight of the man, and all those add up to 0. Now I have a way to find force normal if I need it. In fact, I think that's question B. All right, that's not what they're asking. They want to know, where should the man sit? Hint, anytime they ask for a where, they're asking for a distance, and it is going to require a torque equation. Why? Because torque has a distance from an axis of rotation in its definition. Recall, torque equals RF sine theta. Force equation, sum of all the forces, does not have any distances in it. For torque equals RF sine theta. There we go. Okay, so let's sum the torques. Actually, before I do that, since I've identified my axis of rotation, I like to go along and say, okay, here's the torque caused by the girl. Which way will that turn? That's going to go in a counterclockwise direction. That's a positive torque. The torque caused by the weight of the plank is 0 because it runs right through the axis of rotation that we've selected. The torque caused by force normal is 0 because it runs right through the axis of rotation, so we can ignore that. This is going to cause a torque, that's the torque of the man, and that's going to go in a clockwise direction, so that's negative. So the sum of all the torques, I usually start with my positives, torque from the girl minus torque from the man is equal to 0. Okay, so I want to know where the man needs to sit. By the way, we know that the girl is how far away from the center? 2 meters, because she's exactly on the end. And the pivot point is in the middle, so 4 divided by 2 is 2. So we can go ahead and expand this torque equation for the girl. It would be the weight of the girl, so mass of the girl times little g, times her distance away from the axis of rotation, which is 2 meters, times sine of the angle that is made between the r value and the force, which is 90 degrees. I'll go ahead and write that for beginners here. Sine of 90 is 1. I will start to leave that out. Minus the torque caused by the man. That is mass of the man times little g, that's the force, times the r, which is what we're looking for, and again, that'll be sine of 90, which is 1. And all of those added up equals 0. Now we'll solve for r, and we'll find that r is equal to the mass of the girl times little g times 2, sine of 90 is 1, divided by mass of the man times little g. Is that it? Yes, and time. So, okay, mass or little g cancels, and I basically get mass of the girl, which is, what is her mass? 55 kilograms times 2 divided by mass of the man, which is 75 kilograms, and I will find that to be equal to 1.467 meters. Now, where should the man sit? What does that R that we just found? Now use that to describe where he should sit. 1.467 meters to the right of the fulcrum. There is my answer. Okay. What is the force normal acting on the plank? Well, I will have to go up and use my sum of the forces equals, in the y direction equals 0, that equation right there. And I'll rearrange that equation for force normal, and I will find that force normal is equal to the weight of the girl, which is 55, times little g, which is 9.8, plus the weight of the plank, which was 12 kilograms times 9.8, plus the weight of the man, which was 75 kilograms times 9.8. And I believe I used 9, I may have used 10 but I have 1420 1420 newtons. That's what I show here, but I can't tell if I used 10. Looks like I might have used 10. I did. It'll be something slightly different. This is with G equal to 10. Um, they'll let you use 10, by the way, except for ETA. Don't forget that. One more to go, and then we're done for today. It is sometimes important to determine the location of a person's center of mass. This can be done with the arrangement shown in the figure. A light plank, that is important, I'll explain in just a minute, rests on two scales that read 380 newtons and 320 newtons. The scales are separated by a distance of 2. How far from the woman's feet, they want to know from her foot, is her center of gravity? Okay, so here's this picture. I have to draw some, we're going to draw the plank, whoops, and we're going to um, put the forces acting on the plank, okay? Okay, they told me that this scale reads 380 newtons. That is how hard this plank is pushing downward on that scale, which means that it is pushing back upwards on the plank in the same magnitude. That's third law of pairs, 380 newtons. The other scale on the other end is pushing up, that would be 2, that's 320 newtons. Okay, we know that distance apart from one another is 2 meters, and we'll get to that in just a minute. Now, somewhere is the girl's center of mass, which is her weight, which is going to push downward on the plank. And so we'll put that somewhere here. We don't know where that is. That is the weight of the girl, which is the force of gravity acting on her. I have no idea where that is. Now, do I have to draw a force acting on the plank from force of gravity? No, and why not? This phrase, a light plank, means negligible mass. So we're going to ignore the mass of the plank. Kind of weird because I'm actually drawing the forces on the plank, but force of gravity is not acting on it because we're assuming the mass of it is negligible. So I have a total of 3 forces, and I have been asked how far from the woman's foot is the center of gravity. I want to know this value. Okay, we know this value is, let's see, that's 2 meters. Okay, all right. Now, if it's me, I'm going to pick this axis of rotation right here. Okay, by the way, we know this mass of the girl times little g. They told us the mass of the girl. Yes, 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 they have to. No. Oh, I can find that. I don't have that value. You'll see what we have to do here. So I'm going to pick that as an axis of rotation, and just because when I put this torque here, the torque from the girls, um, that R is the exact value that I'm trying to find. They asked for it specifically from her feet, the left part of her foot. That is moving in the clockwise direction, so that's a positive torque. I'm sorry, counterclockwise. The torque from we'll call that torque 1 based on that is going counterclockwise, so that's negative. All right, so let's write some equations. There's no forces in the x direction, so I can ignore that. I have the sum of the forces in the y direction. I have, I'll call it force normal 1, which is 380, plus force normal 2, which is 320, minus the weight of the girl. All of that equals to 0. So we can find the weight of the girl. The weight of the girl is equal to 700 newtons. It's 380 plus 320. We're going to need that in the next equation. Sum of the torques is equal to, well, I've got one positive torque, torque caused by the weight of the girl, minus torque 1. That is relative to the axis of rotation that I have picked. Now, you can pick whichever one you want. You will actually get the exact same number. Okay. Now, if you pick the center one, let's talk about that for just a minute. Let's assume you pick this middle one. You have no idea where that's located. You don't know how far the force normal 1 is from it, and you don't know how far force number 2 is from it. So that would not be it's not solvable in that way. So, okay, keep going. That is equal to 0. Now I can expand the torque on the girl to be her weight, which we found to be 700, times the distance r, which is exactly what we're looking for. That's the distance away from that axis of rotation. That is sine of 90, so I can ignore that. That's my 1, minus torque from force normal 1, which is 380, times its distance away from the axis of rotation, which is 2 meters, times sine of 90, which is just 1. And I can ignore the torque caused by 320 newtons, which is force normal 2, because it runs right through the axis of rotation. So that's just going to go away. That equals 0. So now I will solve for r, and r will be 1.09 meters. And is that the distance that they're asking for? And because of what I selected as my axis rotation, it is. So that is the end of this lesson. We'll have another lesson tomorrow where I do 2 more advanced problems. You should be able to start your homework from ETA using the technique that was shown here.